Ladies and gentlemen, I welcome you to our presentation and demonstration on ATENA software. We would like to show you the latest news on advanced analysis and design of safety critical structures using software ATENA. So what do we do actually? We develop technology for nonlinear simulation of reinforced concrete structures. This slide summarizes the range of problems that we can simulate with software ATENA, starting from nuclear containments, details about structural reinforcement, or the hydration, temperature development during the hydration of reinforced concrete structures. So the motto of our company is to test your structure before you build it. Test it using the virtual simulation on your computer. Where do we come from? We are a small company located in Europe, in Czech Republic, in Prague. This is the photo of our company at the bottom, and also you see on the left top, on the right top, you see the nice view of the famous Prague castle. So we develop software, ATENA, SARA, and FREED, focusing on advanced modeling of reinforced concrete structures, considering the reliability stochastic simulation. So we have representatives located in many countries all over the world. We are active by selling software or providing consulting services in this area of advanced modeling and simulation of reinforced concrete structures. I would like to use this opportunity also to introduce our new representative in the United States, which is the company X Elastica, located in Boulder, Colorado. Here is the information, email contact, and website information that you can use to contact them if you have some questions or inquiries about ATENA software. So what is the motivation for our work? It comes from practical problems that we often encounter in practice when dealing with reinforced concrete structures. We all know that all of our knowledge and formulas that we use in design are based on experiments. Often they are empirical formulas, and these are laboratory experiments which are typically small sizes and also with limited geometry configurations, like beams, typically slabs, or walls or plates. But in reality, we need to apply these formulas, typically empirical, to simulate often situations which are quite complex, like these embedded steel parts in this very massive reinforced concrete slab. Or nowadays, the architects design quite complex and fancy shapes, which again are quite different from our laboratory assumptions. Nowadays we have the new technology of 3D printing of concrete, which again is something which is quite outside of the scope of our original empirical formulas based on quite simple and small laboratory experiments. So how do we apply this simulation in practice? How does it work often? So typically we model the structure in the computer. We include the reinforcement, geometry of the structure, material properties, and then we load the structure up to failure, and then we check whether we have a sufficient reliability, sufficient safety margin, sufficient safety, kind of a strength safety index. Something very similar how you work also in ACI codes. Well, before I come to practical applications, I would like to show some results from blind competitions, which is the best way how to check whether the model can provide, or the modeling can provide, some predictive information. So I would like to show this famous test from Toronto University, Professor Collins. You see they tested these very large walls and they organized a competition, international competition. Here you can see some results from the analysis with ATENA. So here you see the crack pattern in the experiment. the experimental value was 685 kilonewtons, and at the bottom you see the animation from the results from the numerical analysis, where we predicted peak load of 745 kilonewtons. So here we see the results, how we compare to other participants, and mainly to the experimental data, experimental strengths of the beam. So here you see this red point shows our results. So in there were actually two tests. Once they tested the beam on the right side without shear reinforcement, then they put some ties to strengthen this part, continue with the test to break also the left side where there was some minimum shear reinforcement. So you can see we nicely always were quite close to the experimental result, and also obtained a very good crack pattern. So that's why our predictions were actually the winners of this competition. But we have to understand that it is always not like that. We have to understand that these blind predictions are a little bit lottery, because to be in 10%, which was this yellow zone, to be in 10% accuracy, this is quite a lucky shot. Yes, we have to understand that concrete is quite heterogeneous material, so typically we know that we can predict to around 10 to 20% accuracy. Here we see some results from other competitions, other blind predictions. So all these were always blind competitions. That means we were making the analysis before knowing the experimental result. So you see, I am summarizing here some results going quite long back into the history to 1982. That was actually my father at that time. So you can see that in our company we have a quite long history of working in this area of advanced concrete simulation and modeling, up to some most recent tests from FIB 2023, which was a test on fiber reinforced concrete. So you see we consistently get quite good results, quite good predictions. These gray areas indicate the scatter that was obtained in these competitions. And at the bottom you see some slides of these typical of the structures that were actually parts of these various competitions. So now I would like to show some examples of application. Basically I will show two examples in a little bit more detail. One was precast segmental pre-stressed reinforced concrete bridge, and another one was an application to digital twin approach. That means we combine the numerical modeling with monitoring of the real structure. So let's start with this segmental bridge. So this bridge had some problems after it has been constructed, so that's why nonlinear modeling and analysis was used to investigate the root cause and also to propose strengthening. Here you see the model. We modeled actually one cantilever from midspan to midspan. You see quite detailed model which included the reinforcement, the normal reinforcement of each segment, the pre-stressed tendons, the gaps between the contacts between the individual segments. Here you again see these individual parts, the pre-stressing tendons at the top, so there were some top pre-stressing tendons, also pre-stressing at the bottom, normal reinforcement in the segments, which also contributed some special anchoring reinforcement and anchorages, and also the contacts between the individual segments. Here you see why actually the bridge was investigated. This is the crack. Diagonal shear cracks were discovered soon after the construction was completed. Here you see the results from the simulation, where actually quite complicated, or very exactly the construction process was taken into account and modeled. An important part was that the construction of the bridge was interrupted for almost 2 years, and when the bridge was not fully properly insulated from the top, because there was no the road was not yet there, so the sun was the bridge was exposed to the sun, and this showed to have quite important effect on the propagation and development of these diagonal cracks. So here you see the typical results of such a simulation. Again, we typically load the structure up to the peak load. So on the horizontal axis you see the deflection, and we have one curve for the deflection of the left span, one for the right span, and then at various points we can also look in more detail what is happening in the structure. And this first point, or this yellow point, they indicate the onset of reinforcement yielding, when the normal reinforcement starts to yield. Then these green points indicate when the pre-stressing cables start to yield. But as a critical load for the bridge was decided this point, which corresponded to the situation when excessive or quite large crushing of concrete was observed in the model. So these points with the concrete crushing were always described as critical for the bridge and were used as a maximum load free capacity. Here you see also the view, or the slide shows the strengthening, which was also considered and included in the model. So there were some internal additional cables inserted into the inside of the box girder to strengthen the bridge. And you can see also how the crack width was decreased by application of this strengthening. Well, you would say that maybe the crack width hasn't decreased that much, but that's unfortunately due to the fact that the stiffness of these tendons is not that large. So here you see also the situation, or the slide shows how this analysis helped to discover the importance of this thermal load event, which caused the sudden increase of these diagonal shear cracks. Now another example comes from this digital twin approach. That means we have a model, numerical model of the bridge, but in addition we have monitoring, and this monitoring allows us to create a calibrated numerical model, and then we can use this numerical model to make long-term predictions. As you can see here, this slide shows the situation where we simulate this bridge up to 150 years. So this, what do we see here? This top left figure shows the chloride concentration at the depth of reinforcement. So you see how the chloride concentration is increasing, and you also see how it is affected by the presence of cracks. So the durability model that we are using simulates the propagation of chlorides, and it takes into account the presence of maybe mechanical cracks due to loading. So this bottom left figure shows how it affects the corrosion of the reinforcement. So the blue is the intact reinforcement, and as the times goes, you see corrosion development in the reinforcement, and again you nicely can see how it is how we have higher corrosion levels. The highest corrosion is this red color at the areas of the cracks. This right top figure shows the cracks inside the structure, which is one of the unique visualization options in our software. This shows the crack width, which is also a very interesting and useful output quantity. And here we see a special figure showing the development of cracks at the bottom surface. So how do we work with this analysis? We always load the structure to certain to certain load level, and then we apply the chlorides. So that means we assume that there is a attack from chlorides on the surfaces, outside surfaces of the structure, and as these chlorides induce corrosion in the reinforcement, we see an increase in deflection, and which you can see on this figure as this small plateau. And then always after certain time we load the structure up to failure. So here we have one curve, red, the green one corresponding to original bridge when it is 0 years old. Then after 50 years, the blue curve. After 100 years, we see significant reduction of the strength, and very significant reduction if we go to 150 years. And we use some global safety formats, and we can plot this load carrying capacity of the bridge in time. So these are the typical graphs that we obtained from this analysis, where we combine this digital twin approach, combining monitoring and nonlinear analysis. And we see how the strength of the structure indicated by this design strength decreases in time, and we can say, let's say about 125 years, we are reaching the service life of this structure. So this is a method where we are applying this nonlinear analysis for the structural health monitoring. Combined, of course, important is to combine it and have it calibrated and controlled by some by monitoring support. Now I would like to finish my presentation with a few more examples from other structures. So here's an application of nonlinear analysis to high-rise buildings, to some special buildings like this UAE pavilion, United Arab Emirates pavilion at Expo 2020. Here you see the model of this very nice architecture, very pleasing building. The roof, which seem to be like the wings of a falcon, which should represent the wings of a falcon. And the critical point there was this modeling or check the strength of these very large walls with long span, and at first they showed some deficiency in shear capacity, so that's why in the final design the shear capacity or the shear reinforcement was increased here. Another application, very interesting one, is to this offshore wind energy, wind production, electrical energy towers for electrical energy production by wind. Here you see the model, and here you see the development of interior cracks due to the extreme loading event. Now I would like to show a little bit some slides from the software to give you some idea how this actually works in practice. So we have our new generation of our preprocessor, which is called ATENA Engineering 2024, where you can model the structure. Basically, you create a geometric model of the structure. In this case, it is some beam, prefabricated beam with openings. You can model exact location of reinforcement. There is some strengthening, because in this case the beams show to have insufficient strength, so they have to design some strengthening, which is here by these additional steel plates. Then some loads are applied, boundary conditions. These circles indicate some monitoring points, because we would like to follow the deflections of the structure and the reactions, the total loads applied to the structure. Loads here you can see, main load is by application of some distributed loading from the top. So this very quick video shows you some of the unique features. This is actually exactly the screen that you see when the software is running. So this is one of the unique features of ATENA, that immediately as the program is calculating, you can see how the structure deforms. This allows you to quickly recognize any modeling errors and correct them. It gives also a very nice insight into the structural behavior. I have to admit that sometimes when I want to understand the structure, I look for a few minutes how the analysis is going, and this provides me really deep and much better understanding what is going on, what are maybe the weak points of the structure or strong points, or where the structure can be improved. Of course, now I render this animation a little bit faster. In reality, this analysis will take about 1 hour. So now I want to mention some of the recent development, because we are using this opportunity of the ACI 2024 convention to introduce this new ATENA version 2024. So one of the new features there is the possibility of integrated Python scripting, which enables you to actually build special models or special plugins for some applications. This is, for instance, the plugin for a specialized modeling of hydration heat development, like you see here, that you can use to check the hydration for some specific geometrical assemblies. Here it is for more complex situation where we model the hydration heat development in concrete structure in 3D. So all these things are now available in the new version of ATENA. And also one of the recent applications is that, as I mentioned before, is the modeling of 3D printing of concrete. So we can actually model the construction of the 3D printing buildings, and main reason for such a simulation is to check to whether we don't have a collapse of the structure during printing, which very often happens. Like in this situation, you can see here that there is quite excessive deformation, but because the speed of the printing was optimized not to have a collapse of the structure at this point or any other of these points with these curved wall geometries. So with this, I would like to finish my presentation, and for those of you who are attending ACI Spring Convention in New Orleans 2024, you are very welcome to come to visit us at our booth in the exhibition area. Our booth number is 500. So with this, I thank you for your attention, and I'm looking forward to seeing you in New Orleans.
ATENA program produced by Chervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.